Welcome to lecture on the Fourier transform of the rectangular pulse. This fundamental signal pair provides critical insights into time-frequency relationships that form the basis of modern signal processing, communications, and system analysis. The importance of this transform pair cannot be overstated. It represents the most direct illustration of the duality between time localization and frequency spread, a concept that underlies digital communications, spectral analysis, and the uncertainty principle in signal processing. The rectangular pulse is mathematically defined as a function, denoted x of t. This function is assigned a constant amplitude, a, for values of time, t, whose absolute value is less than or equal to the duration, t, divided by 2. For all other instances of time, the function value is defined as 0. This piecewise definition describes a signal of finite duration with abrupt transitions. Proceeding the Fourier transform, the operation is defined by a specific integral. The transform, denoted capital X of f, is calculated as the integral from negative infinity to positive infinity of the time domain signal x of t multiplied by the complex exponential kernel e raised to the power of negative j 2 pi f t with respect to the time variable t. Given the definition of the pulse, the non-zero portion is confined to a finite interval. Consequently, the limits of integration are effectively reduced. The expression simplifies to the definite integral from negative t over 2 to positive t over 2 of the constant amplitude a multiplied by the complex exponential e to the power of negative j 2 pi f t. The integration of the straightforward exponential function is then performed. The solution equals to amplitude a multiplied by the expression e to the power of negative j 2 pi f t, all divided by the constant term negative j 2 pi f. This result is subsequently calculated at the upper boundary t equals positive t over 2 and subtracted from its evaluation at the lower boundary t equals negative t over 2. Executing this evaluation yields a new expression a divided by negative j 2 pi f multiplied by the difference of two complex exponentials. This difference is e to the power of negative j pi f t minus e to the power of positive j pi f t. This particular difference of exponentials is recognized as being proportional to a sine function. Application of Euler's fundamental identity that e to the power of j theta minus e to the power of negative j theta is equivalent to 2j multiplied by the sine of theta. Using this relation, the previous difference is rewritten as negative 2j multiplied by the sine of the quantity pi f t. This substitution is made into the main expression. The Fourier transform x of f is now expressed as a divided by negative j 2 pi f multiplied by the factor negative 2j sine of pi f t. A systematic simplification of constants and imaginary units is conducted. The negative signs multiplied by 2j in the numerator and denominator cancel each other. Following this cancellation, the final simplified result is obtained capital X of f equals the amplitude a multiplied by the sine of pi f t divided by the product pi f. For compact notation and conceptual clarity, this result is commonly expressed using the normalized sinc function. By definition, the sinc function is given by sinc of argument x equals sine of pi x divided by pi x. Therefore, The complete Fourier transform pair is presented as the time-domain rectangular pulse of amplitude A and duration t, corresponding to the frequency domain function A multiplied by t multiplied by sinc of the product f t. The derivation is thus concluded. It is important to note that two common definitions of the sinc function exist in literature. The one used here, with a pi factor inside the sine function, is standard in signal processing and communications theory. The sinc function has characteristic a magnitude spectrum with a main lobe and decreasing side lobes or zero crossings frequencies at integral multiple of 1 over time period, whereas the phase spectrum that switches between 0 and plus or minus pi radians at zeros of amplitude spectrum. The magnitude spectrum is the absolute value of this sinc function, scaled by the pulse area A times t. It has maximum value at frequency equals 0 because sinc function has maximum at 0 argument. This derivation establishes the fundamental relationship. Confinement in time leads to spreading in frequency. The rectangular pulse, with its sharp discontinuities, requires infinite frequency components to be perfectly represented, though these components decay proportionally to 1 over frequency. The majority of the signal's spectral energy is concentrated within the main lobe. While the spectrum theoretically extends to infinity in frequency, the amplitude decays proportionally to 1 over f, meaning higher frequency components become progressively less significant. The significance of the rectangular pulse and its corresponding transform is observed across numerous technical disciplines, providing foundational concepts for analysis and design. In signal processing, the pulse serves as a critical model. It is employed as an approximation for real-world sampling circuits, such as sample and hold operations, where the spectral spreading effect revealed by the sinc function is directly witnessed. In digital communications, the pulse represents the simplest form of non-return to zero, or NRZ, signaling, forming the basis for understanding challenges like intersymbol interference. Furthermore, its frequency domain profile is utilized as an idealized model for low-pass filter responses, with the Gibbs phenomenon being prominently illustrated when such a response is truncated. From a system analysis perspective, the pair is indispensable. The rectangular function is treated as a fundamental window in time domain analysis, with its sinc transform demonstrating the inherent trade-off between temporal resolution and spectral leakage, a critical consideration in Fourier analysis. The pair also provides a clear, visual representation of the convolution theorem, where the convolution of two rectangular pulses is seen to produce a triangular function in time. Most profoundly, it offers a quintessential example of the uncertainty principle in signal processing, illustrating that a signal cannot be simultaneously confined to a finite duration in time and a finite bandwidth in frequency. In the realms of mathematics and physics, the importance is equally established. The Rexing pair constitutes one of the most elementary and vital Fourier transform pairs, forming a cornerstone for the theory of distributions. In physical optics, the far-field diffraction pattern produced by a single, uniformly illuminated slit is described by the squared magnitude of the sinc function, directly linking this mathematical concept to observable wave phenomena. The practical utility of the rectangular pulse and its transform is evidenced by its widespread application across diverse engineering fields, are summarized in table. In the domain of digital circuits and communication systems, the rectangular shape is commonly utilized to represent idealized clock signals and digital data pulses. The associated sinc spectrum is critical for analyzing bandwidth requirements and potential interference. Within radar and sensing systems, The properties of the pulse are exploited in techniques such as pulse compression, the matched filtering operation, which optimizes signal-to-noise ratio for known pulse shapes, relies fundamentally on the characteristics of the pulse and its transform. In imaging and optics, the rectangular function models the effect of a finite aperture or a single pixel's sampling area. The resulting sinc function point spread function describes how a perfect point of light is blurred in the image, defining the system's resolution. For audio and vibration analysis, a rectangular window is applied to segments of a continuous signal to perform short-time Fourier analysis. The spectral leakage associated with this window, a consequence of its sinc-shaped frequency response, is a key factor in spectrum analyzer design and interpretation. Thus, from the transmission of digital bits to the formation of images and the analysis of sounds, the implications of this fundamental signal pair are extensively encountered in technological applications.